and should appear in 1 year, 2 years, 3 years. They made a prediction about this source. 2014, 1, 2, 3, 4. 2015, the prediction here. So this was in the past. This had yet to arrive. This had already arrived. This we are seeing here the future. What is left? This is now, this is the past. This is also the past, but not so far. And here, there is. On January 2015, December 2015 was in January. 1 year before was seen this one, and this was seen 1 year after. So at the right, almost basically at the right time, arrived the other one, which is really a spectacular confirmation of the fact that the space is warped. Light takes its own path, takes its shortcut, finding the the best way to arrive to us, and sometimes gets late, a little bit late, a little bit early, and the universe is blinking like a Christmas tree in front of us. And we see this. So, mass stretches space. But what about time? That's the other fascinating point. Because it's not entirely convincing, this stretching of space, to explain really why we are sitting and not floating around. What is exactly gravity? We need to think about time. This is an interesting point that you rarely hear. Time is the key. If we close out, space-time means that the universe, physics think in terms of 4 points, x, y, z, the 3 coordinates, and time. If I stand here like that, close your eye, you are not moving. But actually in time, we are moving. Is now, is now, is now. We are moving like hell. You can say that you are moving at the speed of the light in time. The presence of mass makes our movement in time a little bit weird. We move in time at the speed of the light, means that it's like we are on the moon in 1 second. But in the same second, we move a little bit closer to the mass. That's in the field equations. This is gravity. It's the fact that we are falling a little bit to the center of the Earth as time flows that makes us sit. Clear? It's fascinating. It's our rush through the time that by a minimal amount puts you down. The closer we are to the mass and the bigger is the mass, the more the effect is strong. And this is why at the end you start having crazy stuff like the black holes. They fall and fall and fall. And you change the property of time, of distances. But we are just at the surface of this. We have a tiny bit of effect, is what we call gravity. So think about mass that bends space, gravitational arcs, and this strange distortion of time, which is what we call gravity. They are all related in this extremely elegant and actually simple equation that Einstein wrote. It's simple to write. Then if you want to use it to get out stuff, it takes forever. But this is the idea. So I wanted to make this point because it's always strange to think what is really is gravity. Is the fact that time warps us to the down. And how to visualize this? I was thinking, how can you say? I mean, this is at some point you need to be creative and a little bit of an ass. Salvador Dali maybe tried to do that. Right? This stuff, like certain works of De Chirico, at MoMA as well, they came out in these years. When these ideas, when these visions started, this artist had to deal with that and try to explain that time flows in a different way when you are in a gravitational field. So this is what astronomers could do before. Now we are in front of this gravitational waves detector. We see this warping not up there are clusters of galaxies. It's here. It's here. And we can measure these two lasers that dance back and forth, which is a miracle. We are, as astronomers, still left with new enigmas, of course. The last slide was perfect. These are new set of beasts that we are measuring. Nobody had predicted that black holes can be so big. I mean, there are black holes which are huge, the one at the center of the galaxy. They are completely different histories. But stellar black holes like this, they are a little bit too big, 36 and 29. I don't know if these are the masses that you had. Yeah, because they go to 65, right? How much? 60 something. Plus 3 masses, plus 3 get going mass. These are big numbers. It's very hard, believe it or not. Between 20 and 30, we get crazy about that. It's 30, these are big numbers. It's very hard. Black hole is the leftover of a dying star, a big dying star. I should say probably that the entire, let's go back to Newton, okay? Let me use the forbidden word, the G word, gravity, okay? I use gravity, forgive me. So, the entire story of the cosmic evolution, if you like, from the physics point of view, is really this fight against gravity. Mass very easily gets together because there is gravity, and there is nothing that can really resist gravity. There is not like electrical forces, which is positive and negative, or the nuclear forces that die immediately and nobody feels. Gravity is there, calls everywhere, hey, come here, and things concentrate to the center. So it's an entire fight against putting things together. And nature has many ways to resist. Electric forces, crystal forces, rocks. A rock is a rock, has its own shape, it's not getting smaller because the chemical forces say, okay, stop gravity, you are not big enough, I can resist, I take my shape. An asteroid, if you look at the picture of an asteroid, is a nice rock, the comets. When you get a little bit too much gravity, the forces start to feel uncomfortable. Well, that's a lot of push. So what they do? They change shape, become round. The moon is round, the earth is round. So the roundness starts telling you that it's okay, it's still resisting, but is actually feeling the tendency of, has to adjust the shape. It's not like a rock that is insensitive. Round means gravity starts to dictate a little bit, at least the shape. Then you put more mass, and then you start breaking the crystal is gone, becomes hot. It has to move, which is a gaseous planet, Jupiter. Then you put more mass, and the gas gets very hot and may become eventually so hot at the center that becomes a star. It starts burning hydrogen and burns hydrogen. And finally there is a nice source of heat, of energy, and gravity has to stop and stays there for 10 billion years, our sun. Eventually hydrogen runs out. Okay, the star says, gets colder, smaller, adjusts, starts burning helium. Runs out. Okay, stop helium. Carbon, let's burn carbon and nitrogen. Runs out. Magnesium runs out. Everything runs out, actually sooner and sooner. Iron, you cannot burn iron. Right? At some point there is nothing else. So you really find new ways to resist gravity. And when you run out of nuclear fusions, there are still new tricks. One is electron degeneracy. You cannot put two electrons too close. Pauli principle, quantum mechanics. So the star gets with this gas of electrons that repel each other. It's a strong repulsion. White dwarf. At some point, the gravity can be so strong that the electrons say, okay, I give up. There is another way. The electrons and the protons become nuclei, become neutrons. So you build a structure which is like a huge nucleus, extremely dense, neutron star. When you are more than 3 solar masses neutron star, which is a monster beast, it's not enough. Gravity wins again. And there we don't know what is going on. But we know that gravity must win, and this is what we call a black hole. So at the end of this process, the stars adjust, and eventually, if they are big enough, more than 3, not at the beginning, at the end, because the stars may lose, the star has its own, sweating a lot, big stars. But if they end up having more than 3-point-something solar masses, they make a black hole. They have to start with the 10, 15 solar masses, and they end up as black holes. So to get 36 or 30, something like that, you must start with a huge star, a huge mass, of the order of 100 suns. They have a life extremely short, as stars. They blow, and the black hole is left. And the black hole can go on for the rest of the age of the universe, of course. There's nothing there. The explosion of the star that leaves the black hole, or leaves the white dwarf, or leaves the neutron star. Normally, neutron star or black holes are called supernova, and we see them all the time, right? This is a star captured before, when it's still sweating like hell. So from 100 is going to 90, 80, 70, 30 in a few million years. It's very rapidly. This is the brightest stars of the galaxy, probably. It's a star that is getting almost at the point of exploding in the Carina constellation. It's called Eta Carinae. It's a fascinating object. It shows you how this mass loss, actually the mass loss is important because it's what makes us. Carbon, nitrogen, is where this stuff comes from, right? We are stardust, literally. So during this phase, a lot of good stuff is produced. But eventually there is the explosion. Bam! And at the center of the explosion, a tiny object is left. Can be a neutron star, the nucleus, but if something too big is left, is a black hole. Black hole of 30, 40 solar masses are still huge because the star is losing a lot of material and still having so much left over is sort of incredible. It's beyond our understanding. It's a surprise. We never figured out how to do that.